Okay, so now let's go for the second, which is the equilibrium reactor. And I'm gonna add the reactor here. I'm gonna call it equilibrium. And this is the feed to the equilibrium reactor. And if we connect the output, we will see that we have to connect two outputs. This is a required vapor output, and this is a required liquid output. It's not gonna make a difference as inputs to us, but this is the way it should be connected, so we have to connect it the way it needs. So this is gonna be the liquid of the equilibrium, and this is gonna be the vapor for the equilibrium reactor. And let's see what information we need to define. It's gonna be the same thing that we did before in the stoichiometric reactor. So you have to put the temperature as 675, and we put the pressure as 1 atmosphere. Again, we'll define the reactions the same way, the reactants and the products. So it's ethanol and acetic acid. This is -1, -1, and we have here water, -1, and ethyl acetate as 1. Oops. And here we will see two things actually. This is exactly what we saw in the stoichiometric reactor, and this is kind of very weird to me, because the point of strength in the equilibrium reactor that it can do thermodynamic calculations to tell you how far this reaction can go and how what's the equilibrium composition that you can get out of this reactor. But what you do here is that when you put the molar extent, it's gonna turn out to be a stoichiometric reactor. So it's not gonna make any difference. So again, if I put the molar extent of 100, then I'm gonna do the same for both just to check. So this is the stoichiometric reactor. I'm gonna go for the reactions and change it to molar extent of 100. And so I have both defined the same way for the stoichiometric reactor and for the equilibrium reactor. Again, this is the equilibrium reactor. This is the reaction. I have this molar extent. I'm gonna run the file, and I'm gonna take a look at the stream results. And you have the liquid, it's all liquid, so we don't have any vapors coming out. If I take a look at the product of the stoichiometric reactor, it's gonna be exactly the same. So I have the stoichiometric reactor, and these are the same numbers, the same enthalpies, the same density, the same everything. So I have the same output from both the stoichiometric and the equilibrium. And if I look at the outputs of the equilibrium, and this is again one thing, that you can get the K equilibrium, the equilibrium constant, but you cannot get its value because you didn't ask the reactor to go to equilibrium, so it cannot calculate the equilibrium constant. So I see this is like a waste of time to have this option here to do the molar extent. So I would never do it here because you're ruining everything. Anyways, so if you go for the temperature approach, and this is the point that is important for me, you can get the equilibrium constant. But what is the temperature approach? What does it mean? So you define the temperature of the reaction to be 75 degrees Celsius here in the specifications, and this tells you at what temperature you need to calculate the equilibrium. How far is it from the temperature that you define? So if I put 0, it means that the difference between the temperature of the equilibrium constant and the temperature of the reaction is 0. So I'm operating at the same temperature. I can do the calculation of the equilibrium constant at different temperatures by changing this. And I'm going to go through this after we run this, do this run. So if I do the run, the results are going to be, again, the summary, the balance, and the equilibrium constant is going to be 103. So it tells me exactly what is the equilibrium constant, and this is very useful piece of information. If you go through the stream results to check it, I need to get rid of it now because I'm not using it. Again, it's all liquid phase, and if you take a look at the mole flows, it's gonna be 127 consumed. And producing ethyl acetate, and you have the 59.4, the remaining amount of ethanol from the reaction. Okay, So again, we checked before from this stoichiometric reactor. We took a look at, and this is very useful thing to gather information from different parts. The heat of reaction was negative, which means that it is an exothermic reaction. So what I would expect, according to the Le Chatelier principle that we mentioned before, that this value of K should be higher if I reduce the temperature, because it's an exothermic reaction, it produces heat, so I need to make it at lower temperature so the reaction can proceed to the forward direction. So let's, for instance, go to this reaction, and then instead of operating at the same temperature, I'm going to make it at -30. -30 means that the temperature that's going to be operating at is 75 minus 30 is going to be 45. Okay, and I run the file, and I take a look at the results, and you see the K equilibrium, it's at 45 degrees and it's 186, which means that it gets higher, and it agrees with what we said before. Again, let's look at the stream results, and from the stream results you can see that for the mole flows it's consuming more ethanol than it used to do before. And I have now two phases, liquid and vapor phase for the equilibrium reactor. But the point that I want to highlight is that the amount of both these two streams is higher than before, and the amount of ethanol that's remaining is not as high as before. Okay, so this is something that's it's very useful to check. Again, let's do one more check and see if I do the reaction at higher temperature. So it's going to be 30 instead of -30. So I'm operating at 75 plus 30, it's 105 degrees Celsius. Take a look at the results at the K equilibrium. It is 60, almost 64, which is way less than the 103 that was at 175, at 75 degrees Celsius. So if you take a look at the mole flows, you'd see that the conversion is way less than before. I have 70 moles that are not reacting, which is higher than the number of moles that were not reacted before. So the main output that I can get out of this reactor is the equilibrium constant and the equilibrium conversion, which is very useful piece of information actually. So this is all for the equilibrium reactor, and we will go through in the next video, inshallah. See you then. Goodbye.